All right, hey everybody, thank you for attending. As Matt mentioned, today we're going to be discussing cost-efficient LLM serving with RayServe. My name is Tanmay. I'm an engineer working on Anyscale Endpoints. This is my colleague, Cade.
Hi, I work on Ray Core and LLMs Anyscale.
And today we're really going to be diving into some of the technical details that make RayServe the most cost-effective solution for doing LLMs at scale and in production. So for a little bit of background, as many of you already know, Llama 2 is like the leading OSS LLM right now. The whole community has been jumping on the wagon, and it's been growing extremely fast. But there's still some challenges in terms of deriving real business value from Llama 2. And the biggest challenge that we're going to focus on today is that Llama 2 is really expensive. The last few months, at Anyscale, we've been optimizing RayServe for LLM inference to address this problem. And the result of this optimization has been Anyscale Endpoints. If you remember from the keynote yesterday, Anyscale Endpoints is the cheapest way to use Llama 2 70B in production. And since we've launched just a few weeks ago, we've already served billions of tokens at $1 per million tokens, which is the cheapest rate, as we mentioned. So today we're going to break down how Serve uses GPUs efficiently. And one thing I really want to emphasize throughout this entire talk is that efficient LLM serving is a full stack problem. You need to make optimizations at the infrastructure layer, at the serving layer, and at the model layer. And these all need to work together to really optimize your price. Here's a quick diagram of the LLM inference landscape. So across the top here, you can see all of the different categories I had in the previous slide. This includes cross-region and cloud inference, autoscaling, serving, speculative decoding, continuous batching, and other multi-GPU and single GPU optimizations. Most of the libraries in this diagram cover one specific section or two sections in this landscape. And what we're really going to walk you through today is how LLM and Anyscale take you end to end and integrate with a lot of these different players to provide a full solution. So let's start by discussing why LLM serving is expensive, and then we'll hop into two technical areas. The first is infrastructure, where we're going to focus on autoscaling and heterogeneous compute. And in the second section, we'll discuss inference and how you can really get the most out of each GPU and saturate its usage. So let's start with the basics of LLM serving. This is a P4DE EC2 instance. It has 8 GPUs. Let's say we want to serve these 3 models on these 8 GPUs. The small blue square there is a Llama 7B model. The green square is the Llama 13B model. And the red square is the Llama 70B model. As you can see, each of these boxes are different sizes because each of these models requires a different amount of GPUs to run. When we start these models with Serve LLM, it's going to allocate the models to the GPUs based on the resource requirements. So it might allocate them like this. Then RayServe is going to start an HTTP server on the instance, so that when traffic comes in, say a user asks, how do I make fried rice? And it wants to query the Llama 70B model. This request is going to be routed through the HTTP server to the Llama 70B model, which is going to run inference. And then the response is going to be given back to the user. And this whole setup kind of draws attention to an obvious problem here, which is that we have an unused GPU. And I really want to emphasize that this is a really substantial problem, because GPUs are extremely expensive. So this one GPU for a month would cost $3,000. And this is really not great. So what we're going to discuss for the rest of this talk is, in order to save money, you need to save GPUs. And you need to use the GPUs that you are using as efficiently as possible. So hopefully this gives some motivation. From now, we're going to hop into the autoscaling section and discuss how we can start saving these unused GPUs. So to motivate autoscaling, here's a plot of endpoints traffic over the course of a few days. As you can see, at the peak traffic, we have 3 times more requests coming in than at the valley. And this is a huge opportunity, because this means that we can save 2/3 of our GPUs during off hours and dramatically reduce our costs. So the way RayServe addresses this is it scales each model independently based on the amount of traffic that model is receiving. And it can do this across multiple nodes and across multiple models. Let's go through a quick example. Let's say you start in the morning and there's just a small amount of traffic coming in. As you can see, there's one blue user using the blue model, and there's one green user using the green model. Because the amount of traffic is small, us having a single replica of the blue and the green model is more than enough. But once more users start coming in, we see the need to scale. So now that we have 3 users, say at noon some more users come in, now we have 3 users, one replica is not sufficient. So Serve is going to automatically add a replica of the blue model to meet this additional demand. Let's say we get even more users. So at 3 p.m., a whole flood of blue users comes in. A whole flood of green users comes in. What do we do now? What Serve is going to do in this case is we're going to start a new instance, and it's going to scale up the models that are receiving traffic to populate the new instance. So as you can see, we've added 4 replicas of the blue model and 2 replicas of the green model. And this is sufficient to serve all of the new users that are coming in. Importantly, Serve will not scale the red model. This is to make sure that we're not wasting GPUs on models that aren't actually receiving traffic. So now what happens when the traffic goes down? So let's say we get to the end of the day, and Serve users are starting to log off. So as the traffic goes down, Serve is going to start downscaling these models. So it removes all the extra replicas, and it goes ahead and removes the extra node once that node is released. So with this simple sort of optimization that RayServe automatically does based on traffic, we can save a whole GPU node overnight. And even in this very simple example, we're seeing a 50% cost saving over just allocating a fixed number of GPUs for our peak traffic. So just to quickly recap, Serve automatically scales each of your models up and down based on usage. And this enables you to save GPUs during off hours and have GPUs during peak hours. Next, we're going to discuss heterogeneous compute. And the idea here is that there are many different types of GPU instances. So each different GPU instance has different pros and cons and is effective for serving different types of models. So this is the previous instance I was using in the example before. This is a P4DE instance. But on AWS, there are many different types of instances. Some of them have less GPUs. Some of them have different types of GPUs. And some of them are on different clouds altogether. So there's other clouds. You might have GPUs on-prem, or you might have GPUs in GCE that are not accessible in AWS. So now the question is, how do we utilize all of these different types of instances and all of these different clouds so that we can cut costs as much as possible? So one simple optimization here. Using smaller instances enables finer-grained autoscaling, which reduces waste. So for smaller models, we can put them on the smaller nodes, right? If we put this blue model on the small node, then during peak hours, we can have very fine-grained upscaling. So we only request as many GPUs as we need. And then during off hours, we can have very fine-grained downscaling so that we don't waste even a single extra GPU. On the other hand, for our larger models, we want to use bigger nodes. And this is because bigger nodes are actually cheaper per GPU. It's kind of like bulk pricing. Larger nodes also generally tend to be more performant, and these bigger models require that additional performance to perform to serve significant amounts of traffic. We can take this a step farther, right? Serve runs on all clouds. It can even run hybrid cloud. So let's go through a quick example of that, right? We can have a single Ray cluster that spans multiple different clouds, so that you can find instances in the cloud that is cheapest for you. And depending on your organization, you might have different discounts and deals in different clouds. And you can really take advantage of the best compute you're able to get. So let's take the same 2 nodes from the previous example. Now I can run the small node, the A10 node, in AWS with my small model. And I can run the big node in Oracle, where I'm getting a 50% discount on my GPU instances. Serve, when it receives traffic, is going to automatically find where the model is located. And it's going to route traffic over a VPN so that you seamlessly see your traffic hit the correct model without you needing to worry about where the model is actually located. So just a quick recap. We went through 2 features here. So the first is autoscaling, which enables you to save unused GPUs. We want to have GPUs during peak hours when we need them, and we want to return GPUs when we don't need them. And the second is heterogeneous compute, which enables us to find the cheapest GPUs and find GPUs in the right clouds. Using smaller instances for smaller models and bigger instances for bigger models, as well as cheaper clouds for bigger instances, is going to enable us to really find the absolute cheapest machines for our workloads. All of this also integrates seamlessly with the autoscaling and all the features that Kate is about to discuss next. So next, I'm going to hand it off to Kate, and he's going to discuss how to get the most out of each of the GPUs using model-level optimizations. Here's Kate.
Thanks, Tanmay. Great explanations. So as Tanmay said, I'll be talking about how to get the most out of each GPU with RayServe. These are LLM-specific optimizations that are really system level. So it's really how can we maximize the utilization of the GPU, and how can we reduce the latency for each token we generate. So as Tanmay said before, cost-efficient LLM inference is a full-stack problem. We have to have optimizations at every layer of the stack. Tanmay covered autoscaling and serving, which are great, and we need those, but they're necessary, not sufficient. How do we get more out of each GPU? I'll be talking about two optimizations, one, continuous batching, and two, speculative decoding, that help get more out of the GPUs. So first, continuous batching, it gets 5.5x additional throughput versus naive batching. This comes from the fact that the sequences from an LLM have different lengths. And so if you make naive batching decisions, you underutilize your GPUs. Continuous batching is a way to optimize the batching decisions, get higher throughput, more concurrency for the GPU, and therefore cost savings. The second optimization, as I said, is speculative decoding. And this is to optimize latency per sequence, up to 50%. And then the key idea of speculative decoding is that some models are easier, some tokens are easier to predict than others. And so maybe you don't need Llama 70B to predict some tokens. You can use Llama 7B. And speculative decoding works by having a small model speculate what the large model will say, and then large model verifies if it's correct. In the happy path, if the small model predicts correctly, then you can have the large model emit more than one token per forward pass, doubling the amount of tokens you get. So first off, I'm going to give a quick background on how LLM inference works. So I drew this little diagram here. This is a toy model with 8 total tokens along the x-axis. And then the yellow boxes are our prompt tokens. So if you're a user of ChatGPT, you'll enter your prompt, your question, whatever it may be. Now, the way LLM inference works is it's iterative. Each time that your system queries the model does one forward pass and generates a token. So here, the blue tokens, the blue boxes, are generated tokens. This repeats. And each time that you're asking the model for the next token, it looks back at all the tokens it's previously generated and the prompt tokens. So it's iterative, one token at a time. It's autoregressive. It looks at all the previous tokens it's generated. And lastly, the completion of the sequence is potentially decided by the model. Of course, the model can emit a special token called the end of sequence token, which here we represent with a red box. And because of this, you can see that you have no idea of when a particular sequence will end. So now continuous batching, the motivation. Here are 2 prompts that I put into ChatGPT. The first one is, what is 2 plus 2? I got 10 tokens in response. 2 plus 2 equals 4. And then the second one is, how are neutron stars formed? I got 558 tokens in response. It was a great answer. I gave all the steps of how they're formed. I learned a lot. But you can see here that these have very different lengths. And if we naively batch these on the GPU, we're going to severely underutilize the GPU. Let's look at a diagram to explain what I mean. So here on the left, we have our initial condition, our initial state. And instead of having one sequence that we are continuing, we have 4 different sequences. So sequence 1, 2, 3, and 4. And we've already generated 1 token. And with each iteration, we'll generate a new token. On the right side, we have the end state, where all 4 sequences have emitted their completion token. And you can see that sequence 3, in particular, is very short. It's kind of like the answer to what is 2 plus 2. And sequence 2 is much longer, maybe how a neutron star is formed. And with this naive batching, where we just put things together without thinking about it, we waste a lot of GPU time. So at the very last iteration, when only sequence 2 is going, we're wasting 3 of the available spaces on the GPU. These white boxes represent waste. So this is a toy example, batch size of 4. In reality, you could have a batch size of like 32. And if one of them goes until the very end, but all the others finish early, you're massively wasting your GPU's capability, and therefore the money you're paying for that GPU. So can we do better? Yes, continuous batching. The key idea behind continuous batching is that after each forward pass, you create a new batch. This gives you the opportunity to look if there's any end of sequence tokens, and if there are, remove them from the batch. This allows us to use the empty space and replace it with an empty prompt, with a waiting prompt. So putting this all together, on top here we have naive batching, and on the bottom we have continuous batching. They begin from the same state, the same 4 sequences, and those 4 sequences go for the same number of iterations. But what you can see here, and this is the key innovation of continuous batching, is that when continuous batching is enabled, you can fit in waiting sequences, waiting prompts, while the other one with naive batching is wasting time. So if you look on the bottom, sequences 5, sequences 6, and sequences 7 have been put onto the GPU and begun processing, while in naive batching, the GPU is just waiting for sequence 2 to complete. Again, batch size of 4, this is just to show how it works, but becomes really impactful for larger batch sizes. So now I'm going to talk about benchmarks. We benchmarked continuous batching and the improvement it produces over static batching. So there's 2 naive batching libraries, which I call static batching. One is called Hugging Face Pipelines. This is your very easy to use Hugging Face library. It's not efficient for inference. You should not use it. And it's our most naive comparison. We also have NVIDIA Faster Transformer. This is a research level library which uses C++ to schedule CUDA kernels. And so it's a much more optimized implementation of naive batching. For continuous batching, we compare VLLM against the 2 naive batching libraries. In our workload, we have a model which is 13 billion parameters. It's OPT 13B. And we're running on an A100 40 gigabyte GPU, just a single one. The way we measure the throughput is we generate 1,000 prompts. Each prompt has 512 input tokens, and then with a random number of output tokens, following an exponential distribution. And then we run this experiment 4 times. 1 where we cap the output length to 32 tokens, 1 to 128, 512, and in the largest case, 1536. The idea here is that as we increase the number of tokens allowed, the variance between 2 sequences in a batch increases. When we cap at 32, the variance is very small, and static batching will do well compared to continuous batching. But as we increase the cap and more realistically represent a production workload, then the variance between 2 sequences in a batch is much higher, and we should expect continuous batching to do much better than naive batching. So the results. On the y-axis here, we have a relative improvement over Hugging Face pipelines. Notice that this is a log scale. And on the x-axis, we have the 4 experiments I discussed. And blue is Faster Transformer, the optimized naive batching, and VLLM is continuous batching. We can see that exactly as I said, for the cases when there's less variance in the batch, static batching and continuous batching perform similarly. So VLLM is 2x naive batching in this case. And as we increase the number of tokens allowed in our batch, and therefore increase the variance between 2 different sequences, we see the gap increases. So for naive batching with Hugging Face pipelines versus Faster Transformer, we see a 4x improvement with Faster Transformer in the worst case. And VLLM is a crazy number, 23x over naive batching. So of course, it's really easy to see how the most naive solution is bad. But even comparing against the optimized solution, VLLM with continuous batching is a 5.5x improvement over static batching with NVIDIA's research quality library, bleeding edge technology. This is a high-level overview. It's a conclusion from our blog post. I highly recommend you check that out if you want to understand more. So just to recap, continuous batching. LLMs generate varying length outputs. This causes challenges for efficiently batching them on the GPU and waste time. Continuous batching makes optimized batching decisions and allows you to increase the throughput. And we see in our benchmark a 5.5x improvement over state-of-the-art Faster Transformer and 23x over naive. Next, I'll talk about speculative decoding. And as I said before, continuous batching is a throughput optimization. Speculative decoding is a latency optimization to reduce the latency for each token. So the first observation we'll make is that the difficulty of predicting each token is not equal. So I have two sentences here, the city of San blank, and this means that GPU is blank. The number of tokens that I would reasonably say for the first case is much smaller. Maybe I'll say San Jose, maybe I'll say San Francisco. Whereas in the latter case, the sentence could go many different directions. We don't know what I'll say next. So you could say that you need a smaller model, smaller modeling power for the first sequence, and a larger model for the second one. So speculative decoding, it follows with this idea of using a small model and easier tokens. Just a back-of-the-napkin calculation, a 7 billion parameter model is 10x faster than a 70 billion parameter model. 9 milliseconds versus 90 milliseconds on a single GPU. But we can do this, but how do we know which tokens are easier? Speculative decoding, one way to do this is to have the draft model, the small model, speculate a sliding window ahead of the large model. So some number of k tokens. Usually you pick a small k, like 3 or 5. Now, every time that the small model speculates a new token, the large model will verify the correctness of that token. And if it's correct, it'll emit the tokens as its own. So let's give an illustration of really how this works. So here again, yellow boxes are our prompt. Green boxes are from our small model. So we have k equals 2 in this case, so we've predicted 2 tokens, speculated 2 tokens ahead of the prompt. And now the large model will verify both those. And in this example, it accepted both of them. So now in the verification pass, we also get a token from the large model. And now with a single forward pass, we've gotten a large model token and 2 accepted small model tokens. This process continues. Another example, the draft model continues 2 tokens ahead. The large model accepts the first one, but rejects the second one. And what that means is that we throw away the rejected token and replace it with a token from the large model. We can continue this, and let's say that this time both tokens are rejected. Or better yet, the first token was rejected, and therefore all the ones after it are also rejected. Again, speculative decoding is going to replace the rejected token with a large model token, and the process goes on. So this is another case where both draft tokens are accepted by the large model. And here, at the end of this example, we can see that 5 tokens were speculated by a small model. It's cheaper. And we only needed 4 forward passes to generate all 9 of those tokens. Huge cost-saving technique and latency reduction. So just to summarize, draft model guesses k tokens ahead. Large model scores each of the k tokens. And tokens are accepted or rejected left to right. So benchmarks. We are working on speculative decoding in VLLM. VLLM is an open source library, and we're going to open source the engine for speculative decoding. But it's under development. We don't have good numbers yet. So we will show that there's a few papers on speculative decoding, one by Chen from DeepMind. And we'll show the benchmarks from that paper on the latency reduction. So in this benchmark, they're comparing a 70 billion parameter model with a 4 billion parameter model as the draft or small model. So here is the benchmark in the paper. We can see that on the y-axis, we have token generation time. And with normal decoding, blue, this is 14 milliseconds. This is true if the task is summarization or if the task is code generation. Now, when we apply speculative decoding, we see that the latency goes down by about 2x, or sometimes even more if there's more predictable tokens. This shows that you can actually feasibly get a 2x reduction in your per token latency. And in my mind, this is amazing. So to recap on speculative decoding, some tokens are easier to predict than others. You can have a small model speculate ahead of the large model. The large model verifies the tokens, make sure they're correct. And if the small model guesses correctly, then you can emit more than 1 token per forward pass, directly reducing your per token latency. OK, to finish out our talk, I'm going to tie this all together into Ray LLM. So as Tanmay discussed earlier, LLM inference is a full stack problem. Cost efficiency requires great cross-cloud, autoscaling, serving. It requires continuous batching, speculative decoding, and other optimizations we haven't discussed today. Another thing is that open source LLMs move extremely fast. I'm sure you all are familiar. frequent innovations released on Hugging Face, and really to win, you need flexibility and developer speed. Otherwise, you'll be left behind. So going back to this high-level LLM inference landscape, we have all of these optimizations in these different libraries. Some of these are open source, like VLLM. Some of them are closed source, like DeepSpeed, MII, their proprietary service. And because this is full stack, we really need a way to package this all together in one place. And this is why we built Ray LLM. Ray LLM takes the best optimizations from each area in open source and packages them together into an easy-to-deploy solution. The idea here is that you can combine all your cost-saving features and make it easy to deploy. And you don't have to update all your libraries with all the features. So you can rely on like Ray Serve for serving and VLLM for the other ones. So as I said, Ray LLM will integrate with LLM engines like VLLM, combines the best optimizations across open source. And because Ray is Python, it's extremely flexible and high development speed. You can support any Hugging Face model, and Ray makes development to production extremely fast. You can own it end to end. All right, that's our talk. Thank you. Yeah, we have 4 minutes for questions.
Yeah, we'll just go right here.
Thank you. I have 2 questions. Which parts of the ones you mentioned in this talk are not available in open source? And then the second question, in the speculative decoding, seems like we're calling the larger model anyway. So how does it actually save the latency?
Good questions. Do you want to take the first one?
Yeah, I'll take the first one. So the first part of the talk, all of that is basically available in open source with Ray Serve, except for multi-cloud. So the part where you can operate over multiple clouds, that's only available on Anyscale. For the second part of the talk, both of those pieces are going to be open sourced, but right now aren't yet available in open source. So for the most part, you can access a lot of this in open source.
Yeah, so the key idea is like if VLLM has continuous batching, which it does, we can use that on Ray. And the second question was, how do we get speed up if we have to ask the model every time? So the way it works is that you can actually have, let's say you have 2 speculative tokens. The large model can actually score those in parallel to accept or reject them. So you can do a single forward pass, which is your expensive operation, and you can get the output whether it accepted or rejected each token in the sequence. Happy to go with more details after the talk.
Thank you so much. It's a great talk. I have a question regarding the auto-scaling in the sense that when loading the language model checkpoints, for example, the 70 billion, it's really gigantic and takes a lot of time for the I/O. Do you pre-warm the containers for those, or how do you handle this cold start problem? Thank you.
Yeah, I'll take that one. So in open source, the way this works is that we just start a new node, and we pull the container, and we load the model. So it's exactly what you're describing. There's like overhead there, and pulling the containers is slow. Loading the models are slow. On Anyscale, we've put in a lot of optimizations to make this really, really fast. So what's going to happen is that the container start is going to be the container pull will be extremely fast. The instance start will be extremely fast, and the model loading from S3 will be extremely fast. So the end-to-end time for getting that new model on is going to be like on the order of like less than a few minutes, right? So I think that we can get a lot of that in open source, but a lot of the best optimizations are on Anyscale. So.
Thank you. When you say Ray LLM package, all these open source libraries together, does that mean you can just import them? You can pick and choose individual ones, or actually Ray would rewrite your own versions for those individual libraries?
Right. So there's 2 things that you can do with Ray LLM. The first is we have a lot of these models just supported out of the box. So we have pre-written YAMLs and stuff, and you can just run them, and it'll just work. So you install Ray LLM, you install the dependencies, and you just run it out of the box. It'll just work. The second is that we expose an engine interface that lets you customize a lot of these pieces. So if you want to use it with some custom open source library, or if you want to use it with some custom model that isn't supported already, you have the full flexibility of going in and doing that. Does that answer the question? Or?
And just to add to that, this is a brand new project, and we're moving really fast to add things. The best support is with VLLM. That's the engine that we've built. But the interface is there for any engine. OK, I think we have time for one more question. Yeah, and if you have other questions, we'll be here after the talk, and you can come ask us questions.
What's the difference between Ray LLM and the Aviary project? Is it the same thing?
It's the same thing. We renamed it. People were getting confused. So.
Good question.